we talk about transition to 100% renewable energy, but the question we have to ask is, why hasn't it happened yet? What are the barriers? Uh, how urgent is it? Are we really running out of energy? Is the prediction that by 2100, this the end of the century, that we won't have any more fossil fuels, is that really accurate? In order to really understand why 100% renewable energy transition, why it is a vision, and for some people it is a necessity, has to do with understanding consumption and really how much we have, and what really we need to be thinking about in terms of what does 100%, like 100% of what, what is it now? When we look at human beings are using 10 to 100 times more energy than what we need for biological survival. So the basics, we have to understand the basics. Energy is what all living organisms need. We need it in the form of plants photosynthesizing, and then that basically takes energy all the way through the food chain to organisms that can't directly use sunlight to make food. We're one of those species. So we need energy in that way. But the 10 to 100 times more has to do with how much we have moved, how much we move, the kind of work we do, and also us shifting from living in areas where we subsisted. And we're the definition of sustainability, to make do with the resources you have without compromising the resources of other spaces and other people, whether in this time or generations down the line. So we're shifting away from that migration, moving and using more and more resources. That's how things went after the Industrial Revolution. So now human beings have set up this energy demand and this energy consumption pattern. So that is what it is. And we have to look at, okay, we have different forms of renewable energy. We have solar, wind, wave, tidal, geothermal, biomass, ocean thermal, and to a degree, nuclear and natural gas is considered renewable. But coming back to where human beings are, we are the species that has this colossal demand for energy, 100 times more what we need for just biological survival. We have to understand that we need renewable energy, renewable in terms of human timescales, which nuclear is not and fossil fuel is not. To a degree, the sun, yes, created billion years ago, but still we are massively underutilizing solar energy. But the other consideration when moving to 100% renewable energy is that every type of energy has another environmental impact, which could possibly require more energy to solve the problem. So that is part of the reason why this 100% renewable energy hasn't just happened, even if people have been talking about it. We need to consider that there are basics in understanding energy. So there's this talk that we can do renewable because there's just so much solar, it's just out there. Energy is free, it's abundant, but there is still the basics of the universe, and now this is where the science comes in, and we have to consider that the first law of thermodynamics is that energy can neither be created nor destroyed. And that sounds great, because then we have all of this solar, like it's not going to be lost. We're not, why are we concerned about it? But the issue is that even though it cannot be created or destroyed, it doesn't mean that it is created. We can't lose it as a human species, because there's certain processes that we aren't able to recover energy from. So this is the distinction, and this is a reference to the book, the energy textbook, which done by Bent or Orr, and that basically distinguishes between high grade and low grade energy. So high grade energy would be your solar, your wind, your wave energy, which can be converted from one form to another without losing too much of the actual energy in terms of heat or sound. Then you have low grade energy, which is more what we have been doing in the beginning of the Industrial Revolution when it comes to steam engines, like finding a way to convert heat to another form of energy, or basically burning fossils, biomass energy, and we are taking energy that took millions of years to create, and we are burning it, converting it to heat. So 100%, a steam engine is never 100% efficient. When you're burning fossil fuels, there's still air emissions, so that all of that is energy being lost. So we have been doing more of that kind, and we are degrading the energy. So still obeys the first law of thermodynamics, where when we burn something or there's heat, the energy isn't being destroyed, but it is moving from the grasp of human beings, unless we then find another energy source to then pull back in the heat and use it for something else. So this is our issue. We're doing more high grade degradation. We're doing more low grade degradation than high grade high grade use of energy, which would be the solar, the wind, the wave, the geothermal. We should remember that in the distinction of all the renewable energies, all of them except for geothermal and tidal are solar. So the sun is still really important, and capturing sun energy is very important. The other basic to understand is the second law of thermodynamics, which is that heat. This is dealing with the degradation of energy, the losing of heat. That heat is always it's nature. It's not its nature to let us use it. The nature of the universe is disorder, entropy. So heat moves. One place doesn't stay hot. That's like the nature of hurricanes. Hurricanes are moving heat from the equators to the poles. Systems basically tend towards disorder, and that's heat's natural tendency. So with that is showing how it's like this. Once we use energy sources that produce more heat than others, then we're losing access as human beings to energy. But it doesn't mean we're losing it from the whole system, because of the first law of thermodynamics. So those two basics, remember that, and that is why now understanding the efficiency of all the renewable energies, the space that we have, is important. And then at the basic level, our consumption level. There are some scientists and schools of thought that say, like, the reason why we're running out of space and how we deal with consumption is by dealing with population growth. Now, we have to remember as well, we're not isolated systems. Countries aren't isolated, and there's always the politics of who has access to which resources. So how if population growth is a main problem, who chooses which populations don't grow, which ones have grown faster? So that's why when I'm talking about us reducing consumption, it is on our choices, our consumer choices, our consumption choices, and not just a sheer numbers game of certain countries are growing too fast and others aren't. Because at the end of the day, all countries the whole world, we cannot grow exponentially, because Earth is still a limited space. We're still a limited space. The sun is still limited to a degree. So we have to remember that in talking about how we're going to transition 100% renewable energy, how we're going to shift access and resources to using more high-grade energy, and going through each type of energy in each place. If we ultimately want to get back to 100% renewable energy, we then have to look at, like, say, what happens on Earth. Although looking at a hurricane moving heat from the equator to the poles, it's tending towards disorder in the place where there was heat, like say at the equators, because those molecules are moving. The whole Earth still has a system of balance, and we can look at 100% renewable energy country by country in that same kind of way. Like, how does a whole country get balance to be able to use all of the resources around it to sustain itself?